Hello. Welcome to the third and last part of section 7.6 applications to physics and engineering. My goal in this video is to derive the formula for the centroid of a lamina. And I'm going to do this by using the information from the previous video. So let me just remind you what we did, right? If we had 2 point masses, M1 and M2, right? And we put it on the x-axis, so the location of M1 is x1, the location of M2 is x2, and then the center of mass, we called it x bar, then x bar was equal to M1 x1 plus M2 x2 all over M1 plus M2. That was the first thing we did. Then we extended this to having different masses in my two-dimensional situations and say this is M1 located at x1, y1, and then this is M2 located at x2, y2. Let me put another one here, M3 located at x3, y3, right? Then the location of the center of mass, the x coordinate, it was just, well, you can actually extend it to having n masses. So it's the sum from I equals 1 to n of mixi over the sum from I equals 1 to n of mi, and then the y coordinate is just the sum from I equals 1 to n of m1 yi over the sum of the masses, okay? MIs, perfect. And then real quick, let me remind you that if my M1, for example, it's located at x1, y1, then x1 represents the distance from the y-axis, and then y1 represents the distance from the x-axis. And I wanted to remind you of this because we're going to use this now to extend it to the centroid of a lamina. Okay, so then our point here was to find, so given something that looks like this, right? This is a lamina. It can have some thickness, like it doesn't have to be like completely flat. Oh God, that's awful. It can have some thickness here. Let me see, something like that. So what we do is, instead of looking at it like this, we ignore first the thickness for a second, and then we ignore the bottom part of it, and we put it on the XY axis. So let me show you what I mean by that. So I'm going to erase, oh God, that's too much. I'm going to erase this part. Now this is the graph of my function f of x, and then this is my x-axis, y-axis, and this is A, and this is B. Okay, and then we want to find the center of mass now of this region, the region under the curve of f of x, and then from from A to B, and we don't know what A is. So from A to B, that's what we're looking for. We want to know the center of mass. I'm gonna say here, centroid. Okay, well, we know the formula. So we know that the x coordinate for the point mass case, it's equal to the sum from I equals 1 to n of my xi times mi over the sum from I equals 1 to n of my mi's. So m represents the mass, okay? M represents the mass, and then xi represents the distance to the y-axis. So then the idea is we're going to do what we always do. Instead of looking at this whole graph, we're going to split it into a bunch of little subintervals. So a bunch of little subintervals, let me use black for that, a bunch of little subintervals, and then, well, we compute the mass of one of the rectangles and then add them all together, right? So let's see. So what I'm saying is, so say now that I take here my ith, let me take the ith subinterval right here. If I take the ith subinterval, then this right here, if I take the midpoint, this is xi, I'm going to approximate it with my midpoint, right? So it's like up to, let me see, up to here. So then this is the rectangle. Okay, so let's focus on this for a second, right? Let's focus on this for a second. And then, of course, I drew it like this, but you know that whenever we split this into little rectangles, little subintervals, we're assuming that they're super tiny. Okay, so then the thickness of my rectangle is just delta x, right? So this is here delta x, and then the height is just f of xi. I'm gonna call it xi star so that you know it's the midpoint. So let's start by computing the moment about the y-axis, which is if we're looking for the centroid, the x-coordinate of the centroid, then this up here, this is the moment about the y-axis. And then understand what's happening here. The moment about the y-axis, it's given by the sum of, well, the xi's, which again, they represent the distance to the y-axis, and then the mi's are just the masses. So the moment, I'm gonna say moment about y-axis for the ith subinterval, it's equal to what? It's equal to mass times the xi, okay? Now, what's the mass, right? So we first need to find mass of that little subinterval. Well, mass is equal to some density rho times area, and then the area it's equal to, well, still have rho, area it's equal to, as usual, height, f of xi star times delta x, okay? Perfect. Now, imagine now that instead of just having one of them, I have infinitely many of them, okay? Then my ith moment, it's equal to, well, mass, which is rho f of xi star delta x times, it's right here, right? Times my xi star, which is just the midpoint. That tells me that then if I can approximate this moment by taking the sum from I equals 1 to n of, well, rho f of xi star delta x times xi star. And then, as we always do, instead of having an approximation, why don't we just take infinitely many of them? So then I take the limit as n goes to infinity. And then hopefully you look at this and you realize that this is just the definition of the integral. So this is just the integral from a to b of, well, rho, and then that I'm going to the continuum, xi's become just x. So we have f of x times x. Let me put it before here, x, f of x, and then delta x becomes dx, okay? And so now what I'm saying is that this is just my moment about the y-axis. So the x coordinate of the centroid becomes the integral from a to b of rho, I'm going to take it out because it's a constant, and then x, f of x dx, okay? And then if you notice that the bottom here, some of the masses is just the area, right? So one more time, if we have here sum of the masses, then here we go. The sum from I equals 1 to n of mi's is just equal to, well, I have to add all the masses, which is just the sum from I equals 1 to n of my rho f of xi star delta x. So if you take it to the continuum by letting n go to infinity, then the denominator here is just rho times the integral from a to b of f of x dx. And something super interesting here is that you get to cancel the rows, right? You get to cancel the densities. Therefore, and let me make that note in red, centroid, this centroid is independent of the density, okay? That's what this means. The fact that I was able to cancel row top and bottom tells me that I have, it's independent of the density, okay? So this is the x coordinate. Now I need to find the y coordinate. And then again, the y coordinate, we're going to compute using the same formula that we used for the point masses, okay? So let me remind you of that. We have that y bar, the y coordinates equal to the sum from I equals 1 to n of the yi's and then the masses all over the sum from I equals 1 to n of my masses, which we know that in this case, and let me not say equal signs, but just like implications, right? Okay. So now what we have is that this is just bottom is just the integral, so rho integral from a to b of f of x dx. And then we have to compute the top, okay? Now, the top, keep in mind that yi represents the distance from my mass to the x-axis, okay? And this is where we have to understand what's going on. So we go back to our little diagram here, and what we do is we say, well, when we were computing the xi, it was trivial, right? Xi, it's always the distance to the y-axis. Now the problem is that if I'm having my yi and yi represents the distance to the x-axis, where do I locate it? Well, think of what's happening, right? If this is a rectangle, then we expect to locate this right in the center. So it is safe to assume that my yi right here, it's located right in the middle of my rectangle, and this is just, so this is yi and this is just 1/2. This is just 1/2 f of xi star, okay? And that's what we're going to use. So then again, I go back here, and now I can even like sort of take this whole thing with me so I don't forget to write anything. I'm going to take this, why am I so lazy? I'm going to take this whole thing with me and then just change what needs to be changed, okay? So here we go. I'm going to put it here, make it smaller. Down here, erase this part because we know that the sum of the masses is just the integral, it's just the area, just the integral from a to b of f of x dx. Okay, so now I'm ready to compute not the moment about the y-axis, but about the x-axis. So about the x-axis of the ith subintegral, mass is still equal to rho times area. Okay, and then my area is still equal to f of xi star delta x. So this stays the same. The difference now is that I have to multiply the area, my mass, I have to multiply it by yi star, right? By my yi. And then yi we saw is just equal to 1/2. This is 1/2 f of xi star. So then my x moment here, mx becomes, instead of rho x f of x, here I have, instead of having xi, we have 1/2 f of xi star. Therefore, my x moment, when I turn it to the continuum, when I write it as an integral, is the integral from a to b of, well, I still have rho there, which I can take out because it's a constant, and I have 1/2 right here, which I can also take out because it is a constant. So rho divided by 2, and then I have f of xi star, I have two of them, and delta x becomes dx. So then here on top, I have again that this is rho divided by 2, the integral from a to b of f of x squared dx. And again, the rows cancel each other because we see that the center is independent of the density, okay? So to summarize, this is what we have now, okay? This is what we have now. We have that my center is given by these formulas, but I wanted to show you where the formulas came from. It's just the y moment over the sum of the masses, which we represent by the integral from a to b of x f of x dx over the integral from a to b of f of x dx, which from now on we're going to refer to that integral like what it is, right? It is the area. This is just the area under the curve. And then the y coordinate, it's given by, well, the x moment, which is 1/2 integral a to b of f of x squared divided by the area, okay? Now, this is what we had if we assume that we didn't have the bottom part of the region, but if we do have the bottom part of the region, then just subtract it. So then if the region is in between two curves, f of x and g of x, now these are my formulas, okay? These are my formulas, right? Then instead of just f of x dx, we have f of x minus g of x. And instead of having just f of x squared, we have f squared minus g squared, okay? And the reason is, well, think about what that means. If we have here now, if we here have something like this, right? And this is the region. So the top, you can think of it like f of x. The bottom, you can think of it as g of x. And then we have our little rectangles as usual. Then say here, if this is xi star, it starts here, right? And then it goes to here. So this would be, I'm just going to draw it like this. This would be the little rectangle that we're using for the approximations. So then the distance is always f of x minus g of x, okay? Does that make sense? I hope it does. So let's do an example. Let's do an example real quick. Find the centroid of the region bounded by the given curves. So we have that y is equal to 2 minus x squared and y is equal to x. Okay, so the very first part, it's always to find the intersections, okay? So as usual, step 1, let's find intersections. Intersections, meaning 2 minus x squared, it means a different color. 2 minus x squared is equal to x. If I solve this, I get that. What do I get? X squared plus x minus 2 is equal to 0. And this is the case if and only if we get x plus 2 times x minus 1 is equal to 0. And we know that in the real numbers, a product is 0 if one of the factors is equal to 0. Therefore, x is equal to -2, x is equal to 1. Step 2, you don't have to do this, but it's always helpful to just sketch the region so that you see what it looks like, see if the answer makes sense. So what do we have? Well, let's see. So we know that this is the graph of y equals x. And then we know that if we have 2 minus x squared, that's a parabola that opens down. And then here, the intersections are here and here. And again, just because we just did it, this right here, it's -2. This right here is 1. And this is the region that we're finding the centroid of, okay? That is the region that we're finding the centroid of. Okay, so now for my third step, then you can just compute the centroid. So step 3, centroid. And then again, I know that you hopefully know the formula now, but then x bar. So the x coordinate, it's equal to the integral from a to b of x f of x dx over the integral from a to b of f of x dx, which then again, this is just the area. And then the y coordinate, it's equal to 1/2 the integral from a to b of f of x. And I'm lying, right? I have two curves here, but then it's, you see how this just extends to what we're doing. So then here, instead of f of x, it's f of x minus g of x dx. And then area, it's the area in between my f of x and g of x, which we know. I'm assuming that f of x is on top, so f of x minus g of x dx. And then again, this is still the area. And then for my y coordinate, we have that this is just f of x squared minus g of x squared dx over, and then I have a to b, f of x minus g of x dx. And again, I'm calling this my area. So let me find this first because I need it for both integrals, okay? So then a, it's equal to, for both coordinates, I mean. So it is equal to the integral from -2 to 1 of f of x, which is 2 minus x squared minus x, and then dx. And I can do this term by term, so I get 2x minus x cubed divided by 3 minus x squared divided by 2, the whole thing from -2 to 1. So if I plug in 1, I get 2 minus 1/3 minus 1/2. And then when I substitute -2, I get -4. And then -2 cubed, you get -8. So plus 8 over 3 minus 4, divided by 2, which is just 2. So I get 2 minus 1/3, 2 minus 1/3 minus 1/2, plus 4 minus 8 over 3 plus 2, I get 9 over 2. And I need this for my x and y coordinates of the center, okay? Perfect. So now I'm ready to compute my x coordinate. I get that this is just, by definition, my x coordinate, it's equal to 1 over 8, which we know it's 9 over 2. So 1 over 9 over 2, which is the same as 2 over 9. And then the integral from -1 to 2. I'm lying. I think it's from -2 to 1 of x times f of x minus g of x. So -2 to 1 of x times f of x, which is 2 minus x squared minus g of x, which is just x dx. Obviously, multiply them together before you try to compute this integral. So you get 2 over 9. And then integral from -2 to 1 of 2x minus x cubed minus x squared dx. Compute each integral, each antiderivative individually. You get 2 over 9. 2 over 9 times, well, 2x squared divided by 2, you get x squared minus x to the 4th divided by 4 minus x cubed divided by 3, this whole thing from -2 to 1. So I get that this is 2 over 9, and then if I substitute 1, I get 1 minus 1 over 4 minus 1 over 3 minus what I get when I substitute -2, which is 4, and then -2 to the 4th, that is, what is it? -2 times 2, you get 4 times 2, you get 8 times 2, you get 16. So this is minus 16 divided by 4, so you get 4 minus, and then -2 cubed, it's -8. So plus 8 divided by 3. I'm going to simplify this thing. I get 2 over 9. 1 minus 1/4 minus 1/3. And then, well, this goes away. Minus 8 over 3. I get -9 over 4. I simplify this thing. I get -1/2, right? This goes away with this. I get -2 over 4, which is just a -1/2. So this is the x coordinate of my centroid. Let me find the y coordinate. Well, the y coordinate, it's given by, we have 1 over a again, but a it's equal to 9 over 2. So it is 1 over 9 over 2, which is 2 over 9, so 2 over 9. And then it's 1 over 2, the integral from -2 to 1 of f of x squared, so 2 minus x squared squared minus x squared dx. And I compute, I'm just going to stop for a second to just remind you what I'm doing again, just in case you just didn't see the formulas. One more time. This is x, and this is my f of x minus my g of x, right? And then here I'm doing f of x squared minus g of x squared, okay? I just wanted to make sure that that is clear. All right, so moving on, I can cancel this 2 with this 2, and I get 1 over 9, the integral from -2 to 1. Well, if I do 2 minus x squared, if I expand it, I get that this is just 4 minus 4x squared plus x to the 4th, and then minus x squared dx. I simplify this thing a little bit more. Integral from -2 to 1 of 4 minus 5x squared. I'm combining this term with this term. And then plus, hold on. This should be to the 4th. And then plus x to the 4th dx. 1 over 9. Compute each antiderivative individually. I get 4x minus 5x cubed divided by 3 plus x to the 5th divided by 5. This thing evaluated from -2 to 1, 1 over 9. If I substitute 1, I get 4 minus 5 over 3 plus 1 over 5. And then if I substitute -2, I get -8. And then -2 cubed, it's -8 times -5, I get plus 40 divided by 3. And then -2 to the 5th, that is equal to -32 divided by 5. So if I have 5 minus 5 thirds plus 1 over 5 plus 8 minus 40 over 3 plus 32 over 5, I'll get 1 over 9. 1 over 9? 1 over 9 times 4 times 18 divided by 5, so I get 2 over 5, okay? I get 2 over 5, so that is the y coordinate of my centroid. So we go back to our graph right here, right? And that says that here we have -1/2 and then 2 over, like somewhere around here is the centroid. So it makes sense that that is the center of mass of my region. Okay, that's all I had for section 7.6, for this part of section 7.6. I hope you enjoyed it. I hope it made sense, and see you next time.